Dear students, I am Dr. Amir Fawaz Zahoor, and you know that we are studying disconnection approach or retrosynthetic analysis. And previously we studied two group CC disconnections in which we studied 1,3 difunctionalized molecules, and we studied various examples. Today we will consider some synthetically and medicinally important examples of 1,3 difunctionalized molecules. For example, we study synthesis of gingerol, first structure of gingerol, this molecule has again same functionality like we discussed in our previous lecture, and this is structure of gingerol. Gingerol is a natural product which occurs in ginger, and it is known to possess antioxidant properties as well as anti-inflammatory activity and also anti-tumor activity. Now we can see same functionality is present here. In our last example, if we ignore this big R group on both sides, what would we get? We get this. And it is very common for the students that they get confused when R is changed. So basically, we don't have to be confused about big R groups on both sides of the functionality. What we have to see is the actual functionality which we are more concerned about in this case, that is 1,3 relationship. And now we start disconnection. Previously we studied about latent polarities, so we add that here as well, positive, negative, positive. And what is the relation? 1, this is 2, this is 3, again 1,3 relationship, and then we can disconnect from here. As a result, we get this synthone, and here we get this synthone. And for this we know that this is A1 type synthone, acceptor synthone, and its synthetic equivalent or reagent is corresponding aldehyde. Whereas for this, corresponding ketone would be used as reagent. Now synthesis. In this case we can use a base. Here is methyl. If you don't put anything, this corner is also representing a methyl group, so we add base, and we can add the aldehyde, this one, and as a result of this reaction we will get the target molecule. So this was synthesis of gingerol. Now we see next example. Next example is synthesis of doxycycline which is an opioid analgesic, and its structure is this one. So this is our target molecule. In this case, we can see that we have this functionality, and this functionality is basically an acetal. Acetals or ketols are protecting reagents, but here we have, it is an important structural feature of doxycycline, and this can be synthesized in the presence of a carbonyl compound, aldehyde or ketone. This takes place in the presence of acid, for example H+, and corresponding alcohol. If we call it R1, then it would be R2, and as a result we get R2 here, R2 here, R1, so R2. So this is, if R1 here in this case is hydrogen, then it would be called as acetal, and if it is R group, carbon based some group, then it would be ketal. So acetal or ketol can be formed in the presence of acid and corresponding alcohol, and here we have cyclic acetal. So for cyclic acetal we can use diol, for example if we use propane diol here, then we get this. So we can see this is same as we have here, therefore we can use this acetal for our II disconnection here and here, because in the single step both the bonds are formed. Here you can see both the bonds are formed in a single step, so simultaneous breakage of bond or disconnection of bonds from both the sides would take place, and we will get corresponding diol, and now we have to see how we can get this diol. One way to get this diol is through functional group interconversion from this molecule. This ester. So if we can convert an ester into an alcohol, this process is reduction. So we can convert this ester, diester, into corresponding diol. Now this can be further disconnected from this position because it's 1, 2, 3, so this will be disconnection here, and we will get this one. along with that dimethylamine, because it's methyl group, here it's also methyl group, so dimethylamine would be obtained. And this can be further disconnected at this position. This is 1, 2, 3, and this is because alpha beta carbonyls are involved, so this disconnection is also called alpha beta, and as a result we will get this. Along with that, corresponding aldehyde. So this was disconnection. Now synthesis. So we will take this ester. This ester is diethyl malonate, and this comes from corresponding acid named as malonic acid. So this is its ester, and then we will add base and corresponding aldehyde. We have to choose same aldehyde because this aldehyde is on third position of this pyridine ring, so we have to keep that in mind throughout our series. And as a result of this condensation, we will get this alpha beta carbonyl, and this will be then subjected to react with dimethylamine, which would attack here, and this process is Michael addition. And as a result of it, we will get this, and this can be reduced using lithium aluminum hydride. Here we can see corresponding diol has been obtained. Now we can convert this diol into this acetal using formaldehyde, but we have to use some acid. Generally we can use mineral acid or acetic acid for this, but in this case we have this basic group which is nitrogen. Therefore, in order to avoid the protonation of this functionality, we can use Lewis acid, for example BF3. And as a result, formaldehyde in the presence of BF3 as Lewis acid, we can get the target molecule. So I hope you have understood this. Now we see another example. Nitriles are another important class of organic compounds which can be used in aldol type reactions. And this reactivity is particularly useful when nitrogen and oxygen, they are in 1,3 relationship. So we see the example. First, the reactivity of nitriles. In case of acetonitrile, the pK of this hydrogen, for example this one, is 25, and we know that in case of, for example, ethyl acetate, pK of these hydrogens is also 25. So they can be used to generate anion, carbanion here using suitable base. So in the presence of base, they can be deprotonated and they can undergo carbonyl additions as well. So it will attack here, and as a result we get this cyanohydrin. Now we see in a nitrile this functionality is present, and because it is unsaturation, it can be reduced using suitable reagent. For example, lithium aluminium hydride, which is a very strong reducing agent and can convert this or reduce it to corresponding amine. So in this case, this is 1, 2, 3. 3 amino alcohols. They can be obtained using this methodology. So in this case, oxygen and nitrogen have 1,3 relationship, and in this case we can use this aldol type reaction to aldehyde or ketones to get this type of target molecules. Now we see an example, and the example is synthesis of venlafaxine, and in this case we have this molecule. Now this is the structure of venlafaxine, and in this case it is our target molecule. This drug is used to treat depressive disorders, or pain disorders as well. So in the first step, we will disconnect from here, and this will be CN amination, because 2-methyl are adding to an amine group, so carbon is getting attached to an amine, so CN amine, and as a result we will get this one. And this functionality, as we explained earlier, can be obtained using corresponding nitrile. Here methoxy group, OH. So the process in which nitrile can be converted into corresponding amine is FGI, functional group interconversion, and it is reduction. And in the next step we can disconnect from here, because we have just studied that nitriles can also undergo nucleophilic addition aldol type reaction to aldehydes and ketones when they have alpha hydrogens. We have this type of synthone. For that, corresponding ketone would be used. Previously we discussed that for this type of synthone we use aldehyde, because in this we have positive charge, So one hydrogen was present here. If hydrogen is not present here and some other alkyl group is present or aryl group is present which is carbon based, then we will get corresponding ketone as reagent. And other synthone would be this. For this we have this molecule as reagent. This molecule can also further be obtained by disconnecting here. This synthone would be obtained and CN negative would be obtained. For this we can have corresponding alkyl halide Br, here for example sodium cyanide. Now we can see the synthesis. As we know, last step of disconnection is first step of synthesis. So in the first step, sodium cyanide would be added to get our cyano compound, and then in the presence of a suitable base and cyclohexanone, this aldol type addition would take place. So we will get this, because negative charge would be produced when base would be added. So this negative charge would attack here and this O negative would be formed here, and as a result it would be converted into OH upon quenching, and this can be reduced further in the presence of lithium aluminium hydride. And in the last step we can convert it into target molecule using excess of formaldehyde, and we get target molecule. So this was about 1-3 disconnections with various examples, and in this lecture we have studied various pharmaceutically important applications of this reaction, and now we see further. Now we study 1,5 disubstituted compounds. This can be studied using the example. This one. This is 1, 2, 3, 4, 5. So this is 1,5 disubstituted compound, and now we first add latent polarities: positive, negative, positive, negative, positive. So here we have electronegative atom, oxygen. So beneath that we would have positive latent polarity or positive charge, and then alternating positive, negative, positive, negative, positive. And here we can see in both the cases where beneath oxygen we have positive charge. So this pattern, which is again matching or coincident, is called consonant. And we can also use this pattern for our disconnection. Another rule is, a very important rule is, simplicity is the key. When we have a complex molecule, it is a good option to try to disconnect from the center. As a result, simplicity can be achieved. So we try to do that, and here we have positive and negative, so we disconnect from here. As a result, we get positive here and negative here as per our latent polarity. Here was negative, so we have put negative here. Here was positive, we have put positive here. And we know that for this we have corresponding alpha beta unsaturated ketone as corresponding reagent, and here we have corresponding ketone as reagent. Now synthesis. In the first step, we will add base, and in the second step, we will add this alpha beta unsaturated ketone, and particularly this is methyl group, here is vinyl group, so this is methyl vinyl ketone. As you know, during naming of ketones, we can name one substituent and then the other one, and this is methyl vinyl ketone reacts with acetone in the presence of base, and the process is Michael addition because the reaction would occur on beta carbon. This is alpha beta, so conjugate addition, which is Michael addition, and we will get target molecule. So I hope you have all understood carefully. If there is some problem, you can leave your questions in comment box. Thanks.